Hello physics students. In this video, we're going to begin our next topic, energy, and eventually in this topic, we're going to be learning the law of conservation of energy, the main idea of the unit, which is a very powerful idea that allows us to analyze systems as we'll see later. Now, but before I begin though, I want to first explain that the law of conservation of energy, in fact, everything we're learning in this unit is redundant. In other words, if you want to understand and analyze the system, it's actually not even necessary. All that you need to know about mechanical systems can be determined from Newton's laws alone, the very beautiful topic we just finished with. But the problem with using Newton's laws to analyze systems is that things can get very difficult very quickly. Like, for example, we studied inclined planes, objects sliding down a hill. That was very difficult, figuring out the forces, the accelerations, velocities, and displacements. Now imagine a hill that's like a roller coaster curved, with different angles of steepness all throughout continuously changing. To analyze a problem like that would take not just Newton's laws, but also calculus and possibly even calculus using a computer to analyze the motion of that. Too difficult. So physicists devised a new theory, this energy and law of conservation of energy, to simplify complicated systems like that. But again, it's redundant. It was actually derived from Newton's laws. Newton's laws are enough to describe everything. So I just wanted to point that out for people who have more of a philosophical mindset, are interested in how these ideas relate to each other. We'll talk more about it when we get to energy conservation. But before we get to that main idea, that powerful idea, we actually have to learn some definitions before we get to the law of conservation of energy. In fact, we're going to spend 4 videos learning different definitions before we can even talk about that main idea in the 5th video. So today we're going to begin with 2 such ideas, work and power. Now, unfortunately, these terms are terms that you've used in everyday life. Like, for example, you might say, I have to go to work later. Oh, I don't want to do that because it's so much work. So you have used the word, and there's certain definitions that come with your use of that word. And same goes for power. But it turns out that if you use the definitions for work that you've been using your whole life in physics class, you're going to get into a lot of trouble on the physics tests. You have to learn the physics definition of work, the physics definition of power, and forget about all the other definitions. And so what I'm going to do is show you the physics definition, and then I'm going to spend a lot of time with different just conceptual examples to show you how the definition of work in physics differs from the definition of work that you use in everyday life. So you can really see the difference and hopefully get all the physics test questions correct about work. So what is the physics definition? Here it is. So let me pause, give you a chance to jot this down. All right, so the symbol for work is a lowercase w. And it's defined as an equation, right? In everyday life, what is work? Well, it's a job, you get paid, there's money involved. It's usually something you don't like to do, like maybe shoveling, you have to go shovel, right? So you get muscles tired. So all these things are the everyday definition of work that we use. Equation here. What it is a force times a distance times the cosine of the angle of the force between the force vector and the displacement vector. An equation. We'll talk more about it later. Just jot it, hopefully you jot it down. The units of work are in newtons times meters. So you could say I did 10 Newton meters of work, and that's correct from a physics standpoint, but it's customary to rename the Newton meter unit as a joule. in honor of a scientist with his work with energy. This is how it's spelled. You just say 10J would be 10 joules of work that you've done, abbreviated. Another possibility is you might have to figure out the work by figuring out the net area of a force versus distance graph. So here's an example of a force versus, oh, I put X over here. It could be X, how far something moves, but let's just be consistent. The distance. And so what happens is, as I'm pushing something maybe in the forward direction with a positive force, it moves a certain number of meters. And then I push with less and less force. And then while it's maybe rolling forward, I turn around and I start pushing backwards with an ever-increasing force in the backwards direction. So I'm pushing like this, then I start pushing backwards for this portion of the motion. The net work would be the area above added together minus any area below the axis. Okay, so that's what is the physics definition of work. So now let's look at some examples where work is possibly done or not done according to the physics definition. So imagine you've got a job at a construction site, and your job is all day a crane will lift a beam in place, and your job is to hold that beam in place maybe while the glue dries or something because they're gluing it in place. Everyday definition of work, that's boring, you're getting tired, you're going to definitely get paid, right? So it meets the criteria of everyday definition of using work. My job, my work is to hold the beam up all day, okay? Is that work from a physics standpoint? So here's example one. When you hold an object stationary, your distance, the distance the object moves is 0, you do no work, right? You plug in 0 here, you're going to get 0 for an answer. So no, you do not do work when you hold something in place from a physics standpoint. 0 joules. How about another job where, let's suppose you've got bricks in the back of one truck over here, and you're to load them into another truck over here, the same height. So I take the brick here, carry it over here, and set it down into the truck over here. Take another brick, set it down. I do work from an everyday standpoint. I would get paid for that. Do I do physics work? Well, how do you carry something? You do not carry something. When you carry it this way, you do not push it this way. Watch this. I'm going to push this that way to carry it that way. Oops, right? Doesn't work. In order to carry something, what you do is you put your hand up under it to prevent it from falling. So you're pushing this way, and then you move this way, right? So force, distance. What's the angle there? So we have force, we have distance. Oh, it looks like we have work, right? Problem is, look at the angle here, 90 degrees between the force and the displacement. So when you plug in cosine 90, you get 0. Try it on a calculator in degree mode. Cos 90, 0. 0 work to carry something horizontally, okay? So when do you actually do work? Well, in the third example, suppose you're dragging an object. You're not carrying it, okay? So if you're dragging an object, so then it's like on a surface like this, and you've got to pull like this to move it this way. So your force is that way, your displacement is that way. Now, we have force, we have displacement. Check, check, right? Good. What about the cosine? What's the angle between these two arrows? Well, there is no angle, right? This will be like 30 degrees. When they're on top of each other, there's no angle between the two. So no angle, in other words, 0 degrees. Plug in cos of 0 into a calculator and you'll get positive 1. So when you drag something, dragging it over a rough surface, you do positive work in that case, okay? In fact, as long as the angle in the cosine function is 0 or greater but less than 90, like you could plug in 30 degrees here, you'll get 0.86 positive. So that's positive work. Plug in 45, I think that's like 0.71 cosine. Positive 0.71 right here times the force distance gives you positive work. Any angle less than 90, okay? Another example, what about if you have a job and you have to lift something up, okay? Like maybe there's someone building a chimney and they're up on a ladder on a second, and you have to climb up another ladder to bring the bricks up to them. So do you do work in everyday life? Well, yeah, you do work in everyday life. You'd get paid for that. Do you do physics work? Well, when you lift something, you're pushing it up like this, and it's moving this way. So there's your force, there's your displacement. So check, check, right? And the angle between those is once again not 30, not 90, but 0 degrees. They're in the same direction. So you plug in 0 here, you're going to get a positive answer. So this is an example where everyday life definition of work and physics definition of work give you the same answer, okay? Or they're the same kind of concept. They're consistent with each other, I should say. What about lowering an object? Well, let's suppose you're at the construction site and the worker is, the mason is done with, the chimney for the day, and you've got to carry his tools down the ladder. Okay, that's your job for the summer. Do you do everyday life work? Yes, you do. You get paid for that. You know, it's tiring, right? Whatever. Do you do physics work? Well, if you lower something, the first thing you have to realize is you do not push down when you lower something. You want to see me push down? That's how you lower something. If you push down, you're throwing it down, right? No, if you want to lower this in a controlled manner, it's like an elevator problem in the Newton's law unit. You have to hold it from falling. And then you have to let it go down like this. So you're supporting it this way from the falling, but your motion is down. And the angle between those two, if you imagine, how do you swivel these two arrows? You're swiveling them 180 degrees apart from each other. And so, if you plug in the force you exert, the distance you move down the ladder, and then a 180 degrees here, in physics, you do negative work. Maybe you owe your boss money, right? You did negative work from physics standpoint. So another difference between everyday life work and physics work. So physics work can be negative, okay? Everyday life, well, that doesn't really make sense to do negative work. One last example. If you try and slow an object to stop it. So let's suppose you have a car rolling in neutral in a parking lot, and it's just rolling steady, and you want to stop it without using the brake pedal with your own body. So the car's rolling this way. As it's rolling this way, you push that way, right? So you're going like this and slowing it down, pushing that way while the car is moving that way. Well, that's what we got here. Force this way while the object's moving in the forward direction. You're pushing backwards. Again, 180 degrees. And again, you're doing negative work when you're slowing something to a stop. So these are many examples of the concept of what physics work is. So look them over. Make sure you understand work can be 0, positive, or negative. It's all about FD and cos theta that determines the sign and the magnitude of work. If you need a moment, I'll create a pause here to allow you to copy this down. Okay, what I want to do now is just a couple quick examples using this concept. Okay, so So there's the example. The worker is dragging a 100-kilogram wood box over a wood floor for 5-meter distance. And we want to determine the work. So first thing we have to do is visualize and think, is there work done? Is it positive or negative? We need to know the force, the distance, and the angle between those two. So if you imagine you're dragging something, you're going to pull this way. I suppose you could pull up at an angle too, but I'm going to keep it simple. And it's going to move this way. So the first thing that we can do through visualizing is realize that the theta is 0 degrees. So oftentimes they don't tell you. You have to imagine lifting an object straight up. You have to picture that. Lower an object. You have to picture that and, draw the arrows to figure out what theta is. This we know is 5 meters. What about the force? Well, we're dragging a wood box over a wood floor. That should trigger your memory to think, okay, I remember wood on wood. That's friction. I'm dragging across because of friction. That's why I need force. And so we got to calculate the friction force. Okay, so the friction force, first of all, the formula for that is on your reference table, right here, back cover. Force of friction is coefficient times normal force, right? So I start with that. Now, the normal force, well, it's a 100-kilogram box. So why is it need a normal force? Because the earth pulls it down and the floor has to support it. So that force of the earth pulling down is right here, the force of gravity, Fg equals mg. So that's how I always put the m and the g together because I feel that ends up being easier. So the Fn is equal to the Fg, which equals mg. So that will equal 100 kilograms times 9.8 meters per second squared, which equals 980 newtons. So there's the normal force. And then the coefficient. Wood on wood, I have to now go to the front cover of the reference table, right here on the lower right, okay? And what you could see is when you find the wood on wood surfaces, you've got to decide between kinetic and static. So because you're dragging it and the surfaces are slipping past each other, you're going to use the kinetic value of 0.3, okay, not the static of 0.42. So now that we have normal and coefficient, we could get that force of friction, 0.3 times 980. And I believe that's 296 newtons. That's the force the worker has to pull to drag this. Oh, 294, sorry. And now that we have the force required and the displacement and the angle, we can use the work function, which, by the way, is also on the reference table here. However, on the Regents reference table, for whatever reason, I'm not exactly sure, they leave the cos theta off. So it's one of the places where the reference table's incomplete. And sometimes you do need the cos theta. Rarely they put a problem where you actually need to know it's cos theta. Most of the time it's either 0 or positive FD or negative FD, okay? But in this case, we'll just go ahead and use the formula FD. So on a test or Regents, you don't have to necessarily write this when you write out the formula. You could write FD unless you need it, okay? So 294, 4 newtons, 5 meters, and we get our answer of 1,470 joules. We could leave it as Newton meters. Oh, and by the way, I could have done cos of 0 also. Okay, so there is an example. Calculate the force required because of the friction, then do FD cos theta. All right, if you need a moment to catch up, I'll create a pause, give you a chance to catch up. Okay, let me do another calculation example. Let's do a little lower here. Okay, so here's a force versus distance graph. So in the beginning, we're pushing plus 9 newtons, but the force gradually changes to negative 18 newtons. And we want to determine the net work. So the net work is the net area of this graph. Kind of like when we had velocity and we find the displacement, we would first imagine this area right here above the axis between the plot and the x-axis. And then we imagine the area between the plot and the x-axis again, which gives us another triangle over here. And then we can say that the work net equals the area above plus the area below. So area 1 plus, minus area 2. So the first area we can find by calculating the area of that triangle up there, which gives us 1/2 the base of the triangle from 0 to 2 meters, which is 2 meters, and the height, which is 9 newtons. And then what we're going to do is subtract off the area of this triangle right here. And its area will be the base is from 2 to 6 meters, which is 4 meters. 2 to 6 is 4. And then the height of the triangle is 18 newtons. So negative 27 joules. So there is the net work done by this varying force. If you need a moment to catch up, I'll create a little pause here to give you that chance. Okay, so we studied the concept of work, physics work, in detail with conceptual examples and a couple calculation examples. We're going to do one more concept today, one more definition, and that definition is power. Just like work, this also has use in everyday language. Often it means emotional. You could say, the movie was powerful, it made me cry, right? You could say that. That's acceptable in everyday life. You could say it means influential. You could say that business owner is very powerful because look at how he can buy buildings and build new ones or whatnot. So that's power. It means like you can influence people. So these are obviously everyday definitions, and you would kind of know that those don't mean physics. But there is, well, first let me write down the physics definition. Power is defined, again, in physics as an equation. And what it is the work per time, okay? So the units of power are joules per second. So you could say, my power was 10 joules per second. That's acceptable. But it's customary to rename the joule per second a watt, which is abbreviated a capital W. And here's an unfortunate thing in this topic. This W and that W are not the same thing. This is the work, okay? So, and it's a lowercase w. And that's measured in joules. The wattage is the power. And that's where the watts goes, in for P. So there's a W for work, the variable, and there's a W for watt, the unit of power. You have to, unfortunately, keep those ideas separate. So in everyday language, if I could kind of explain what power is, it's how quickly you do work, how quickly you transfer work in a system. So it's nothing to do with strength. And here's the everyday definition that kind of causes a little bit of trouble because it kind of sounds physics-like, but it's misapplying the concept of power. People have these weightlifting competitions. They call them powerlifting competitions. And in a powerlifting competition, there are 3 exercises, I believe. There's deadlift, squatting, and bench press. And if you watch those events, the one who wins the powerlifting competition is simply the person who lifts the most weight. Someone lifts 1,000 pounds. The next person lifts 1,005 pounds. They win. No one ever times the event. And so we have no way to know who's generating the more power because no time is ever measured. So for example, if someone lifts 1,000 pounds like this, lifts it straight up quickly off the floor, and then another person, 1,005 pounds, they're struggling like this, over like 5 seconds they lift it up. They have much less power, maybe like 1/5 of the power, because their time was so much greater, okay? Technically, they lose the power even though they lifted more weight. So that's one that really you have to be careful with. Another definition, or in everyday life, that people use the word power for incorrectly, and it sounds physics-like, electricity. They say the power went out, and what you're buying from the utility company is not power. You're actually buying energy or work. Think about this. If you were buying power, the utility company could leave the electricity off the entire month. And then in the last second, they could blast a bunch of electricity into your house. So much that your TV catches on fire, your refrigerator is burned out, your computer melts. A lot of electricity in 1 second. So they do a big ratio of work per time. And they send you a bill for $1 million. You say, well, the electricity was off all month. They say, yeah, but we gave you a lot of power. We gave you a lot of energy in a little bit of time. We're charging you a lot of money. No, you do not buy power. You buy power times time. In fact, if you look at your electric bill, it's in kilowatt hours. Of course, we use watts and seconds, but your electric bill is in power times time. You're buying joules, in a sense, okay? So that's power, how quickly you deliver work. A couple more definitions that are also on the reference table. Work is FD. So you could say power is also FD over time. Or you could say power equals force times speed. And then if you wanted to, you can add a cosine theta to that formula. Of course, it's not on the reference table, but maybe I'll just go like this so it doesn't get too confusing. And those formulas are right at the bottom of your mechanics section on your reference table. So work is a formula, force, distance, cos theta. Can be zero, can be positive, can be negative. Power is a formula, work over time, how quickly you do your work. Not how much, how quickly. And those are the two definitions for today. Now there's going to be another short video that I'm going to include in the stream. I don't want to put it into this video because it's just going to be too long. Something interesting I did once, I calculated the power of someone who, an athlete who delivers energy very quickly. The thing that I thought of that people do in the quickest, I thought, well, maybe like a major league pitcher. They take that ball and in a split second, 100 miles an hour. That's fast. So I figured maybe that's a lot of power. And what I did is I calculated the power of throwing a fastball at 100 miles per hour. Like this, you wind way back and you put a force time, you put work in, and that baseball goes 100 miles an hour. Then I looked at something else, an athlete who does a lot of force. I looked up like crazy bench press. So this is where someone takes a weight. Let me grab a meter stick here. They're laying down on a bench, and there's a lot of weight on this side, a lot of weight on this side, and they bring the bar down like this, and they put it down on their chest, and then they push up like this. And I watched them lifting, I think it was like 700 pounds or 600 pounds or something, and I timed it, and I calculated the power, and I saw which one was more. The baseball, little thing, anyone could hold a baseball. Who generates the most power, the baseball pitcher or the guy lifted like 500-600 pounds? So that's the other video that I'll include in the stream. Kind of interesting. All right, so that's it for today. Definitions, work, power, formulas, be able to apply them, and I'll see you in the next physics video.